This webinar should be pretty short, so you have more time. We'll do questions at the end. If you have questions, I can see them, and I'll get to them at the end of this presentation. So, interesting topic for me, at least. Decided to write this paper, presented at NCSLI. That's what's attached to the handouts part. If you're watching this later, you can go to the website and get it. I showed you how to get there in the documentation tools. There's under papers, this paper is available. So, being said, this is me. My name is Henry Zumbran, president of Morehouse Instrument Company, visionary of Morehouse Instrument Company. Aim to have a purpose to come to work to help everybody make better measurements and to be the best that we can possibly be. This metrology is definitely a challenging field, as you all know. It's challenging in many ways. Latest blog I'm working on is in reference to NIST 811 and how to use SI units. I see a lot of papers with mistakes everywhere. And so that being said, abstract, look, we're calibrating cable tensiometers. You're here because you're either doing it or you want to learn more about it, or maybe you want to bring a house and somebody has people that are saying, hey, can you calibrate these? They're not that difficult to calibrate, though there are a lot of nuances, and there's a lot of people making equipment out there that's really not suitable for the calibration of tensiometers. And they're used everywhere: engineering, construction, aerospace, manufacturing. Kind of indispensable, right? If you want to check tension on a cable, that's what we have. There's other methods, guy wires. You can clamp and put a dynamometer in line on an electric line, and there's other things. But cable tensiometers are so much easier than most current methods. And what we find is the actual calibration of these things is just riddled with problems. And the real solution is either to set a standard practice in place and tell everybody what you're doing, or better yet, have the contract review with your customer, see how they're using it so you can replicate it. And it's especially crucial because different calibration methods can sometimes lead to discrepancies of over 20%, potentially casting doubt on the equipment's functionality. And we're going to go over all of that today. There's more. Calibration, these are the factors, what we're going to dive into. Calibration method, the techniques that you can use. There's dead weight, there's one with only one fixed point, things are hanging in air. Sometimes people are stacking weights, very unsafe in some systems, and sometimes not the best ergonomically, asking people to lift lots of weight, like 50 pounds, 100 pounds, stack up to 2,000 pounds sometimes to calibrate this. Not good. Cable length, the impact of different cable lengths used during calibration. I mean, some systems only use a 2-foot cable. We had a customer ask for an 18-inch cable. We begged and pleaded not to get this, and then they said we need this, and we ended up doing it. And I wish we would have just said no. It's not the right. There are some times when it's okay to say no, and that's when I do wish we would have said no to. Cable type. There's a galvanized versus stainless steel, and that will affect outcomes. So that should be nothing new. The manufacturers of the cable tensiometers, Barfield, Pacific Scientific, a lot of them will state in their manuals that, hey, this different types of cable will affect and impact the reading. So nothing really new there, just a refresher. The other things might be kind of new. Some learning objectives is we have 3 factors that can impact the accuracy of your calibration. And we're going to compare and contrast different methods used for calibrating cable tensiometers, analyze the impact of cable length and the type of calibration results, which is pretty cool. The Navy gave me some stuff. I redacted some of it, but I have some of the stuff that they have there to show with the research that I did. Basically, we had 3 labs making the same measurements and comparing them all. And then recognize the potential discrepancies between current calibration and real-world cable usage, and that conversation piece, that contract review. Appreciate the need for improved communication between the calibration laboratories and end users. So what are cable tensiometers? Hey, they're devices used to measure tension or force in cables, wires, and ropes. Typically feature a load sensor or gauge that provides real-time tension readings. This one on the right here also has temperature. This Barfield, I had the privilege to get to use this for a lot of testing, and the accuracy spec on it's a lot better than these analog ones. And you can see here, which is interesting, you can even see in this picture, look how the cable's bending more as we clamped onto it. So that's going to have an impact on our readings with 2 fixed points, which we'll get into later. And you know, typically what we're going to see the most is like pilots flying. The more people I talk to, it's that industry, you know, fly by wire. Most often you're going to control a rudder or something else with these cables, and if they're too tight, the pilot might complain, or you could have devastating impacts. But what do? They use a force gauge to react against the cable. There's typically a riser. This riser is shown in here. Specifications for the different risers are typically included with the tensiometer, depending if you need a different riser for different cable size. And then the dial on these is often just a linear scale, number 0 through 100, really, really coarse resolution. We get into that discussion. Look, if these things were good on these analog ones, they would repeat perfectly, and then all we have is the resolution, right, that separates us between the different operators in this room. So resolution becomes pretty important when you have super coarse resolution. And then typically there's a conversion or a little chart that's drawn up to convert the number to a meaningful result in pounds force. Typically, from what I've seen, now we don't calibrate tensiometers. We make equipment to calibrate tensiometers. We don't do it in-house. We could. We just never got into it. We have all the cables. We have everything else. Maybe we should do it. Calibration often done by loading the same force point several times. Seen 6 to 7, sometimes I've seen 5. Minimum is at least 3. And you need multiple readings because they don't really repeat as well as you would think for the coarse resolution. And they should be calibrated against the use of should be calibrated based on use and other factors. Some common problems: easy visual inspection, physical damage, overstretching of the spring, which can happen when the correct riser is not installed for calibration, corrosion and damaged risers. So yeah, so if somebody puts in the wrong riser, you can break it pretty easily. And sometimes people do not pay attention, so it's part of your procedure. Make sure the technician select the right riser, assuming it has one. Some of the digital ones do not. Pulled this from the old web. Some calibration procedures may be questionable. Here we have, when I did a Google search, it said a common method is fixturing one point of the cable and stacking weights, or even filling a bucket with the appropriate amount of weight to generate the force. Now we have all kinds of problems with we're just going to fill a bucket with mass, right? Do the correction for density, air, both material and air, do the correction for local gravity if we want to generate a force. There's lots of different things that might be wrong with this method, and we're just going to attach something to a beam in a building and go to it. I don't think auditors are going to like that too much, though you can decide if you think the bucket method would be metrology sound and would pass that audit. I'm saying most auditors are going to say no, though who knows. So typically when we do anything, we deal with 3 things: the right requirements, equipment, and process. And then it's, what do we need to accomplish the task? Does cable tensiometer calibration affect the type and length of the cable used? Yeah. And then you have several variables in this case that can influence the readings. Standard are the methods used for calibration, length of cable, and the type of cable. So pictured to the left is our machine. It's a 2,000-pound force machine. It's over 5 feet. It can accommodate cables up to 5 feet. There's a clear shadow resistance safety shield to protect the operator. Some systems have none of that, so if the cable snaps or they use the wrong cable, guess what? The operator's in it's a pretty nasty situation. I always think of Indiana Jones, and if you've watched those movies, you're going to get a scar on your face. I think the 3rd one, he got hit with he got cracked with he got cracked with, I believe, a whip, and scarred his face. And the truth was, Harrison Ford was in a car accident. That's why he had the scar under his chin. Though, yeah, it's going to do some damage, and it could potentially take eyes out, take other things, scar, could even result in death. depending on what the force it breaks and how it breaks. So the goal is that you have a safety shield. More than likely, it breaks, and if you're in the way, you're going to have a pretty nasty scar, and it's going to leave a mark. And anyway, the tensiometer also eliminates the need to carry and stack weights. Includes clevises for calibration. Everything comes with it. You have multiple load cells. You can do all kinds of stuff with that. Load cells, handheld force gauges, all the other things and everything you need to do. We put a lot of work into designing that. Expanded measurement uncertainty, typically around 0.5 to 0.1% of applied force, depending on the resolution of the UUT that impacts that best existing device. Right equipment also consists of cables at least 3 feet or greater from defects, which we'll talk about. That means the cable should lie flat and not have any bends or kinks. So here's the first thing that we want to really highlight here, bring attention to it. If your standard cables to calibrate these have bends or kinks in them, you're going to get different results. That cable should be replaced ASAP. I know the tendency of some labs is to just keep using the same cables, though it will drastically impact the results. Eric Johansson and some of the other ones, those that don't know him, J&J Labs, he brought this up at an NCSLI meeting, and in the agreement, the consensus agreement that, yeah, bent cables are no bueno, no good at all. And then some systems use cables that are 18 to 24 inches, and these shorter cables almost always lead to different results. So the machine and method, and this is what I'm going to talk about, because there's 2 different ways to do this. And primarily, dead weight has been accepted for many years. As long as I've been around metrology, which is at least 25 years, that dead weight method has been accepted. And that's hanging dead weight avoids hanging dead weight avoids introducing additional tension, as clamping the cable does not affect the measured force. I'll show you more about this. And then machine calibration with 2 fixed points. So you have 2 fixed points, you clamp the cable, guess what? You shorten the distance, create more force. So clamping the cable shortens the distance between these and then introduces additional tension. And other machines exist that lie vertical, some lie horizontal. They wouldn't really lie, they stand vertical or they lie horizontal. Yeah. So those machines might work. There's different ones that have been discontinued over the years, probably because they don't work. There's other methods to back calculate torque. Lots of errors to try to back calculate torque to convert a force and know the length. That's something else that I don't think is very good. So dead weight calibration, highlighted here. You see this, 1 fixed point. This is our a drawing of our dead weight cable tensiometer. 1 fixed point, tensiometers clamped, weights just float in the air. So this eliminates the need to secure cables to beams and manually hang weights. The design also prioritizes safety and simplifies the calibration technician's work. Operator secures the cable and selects the desired weights up to 2,000 pounds. They can just flip a switch, the weight's applied. The cable tends to stretch with more weight, so there's a jack to lift the system and make sure that nothing is touching. And then we have this other machine, and other people make similar machines. This is a Morehouse, our part number PCM2MD-T1. 2 fixed points, we show these in the red circles. So what that means is basically as we clamp the cable, there's going to be more tension produced with it. And I'm going to show you some numbers with that. And one of these points is attached to a more solid fixture in the load cell connected to the jack, and the other is connected to the top where there's a spring. The spring can either be set up to very rigid or have some flex. Now, if it has some flex, we typically find that this machine is not very good for 10 pounds, 10 to 20 pounds. Sometimes you can get a 20-pound reading, but really, really low tension because of that deflection is you often need to do something else. And you can hang weights. We have other things that can be done. In any case, most people aren't measuring that low. From my understanding, most of these start at 20, 40 pounds. Although there are some small ones. A fixed point shown in the red eliminates the need to secure cables and beams. The design prioritizes safety, as I said, and you can go up to 2,000 pounds. basically there's a screw here that you turn the wheel and you generate force clockwise and counterclockwise, so you can do compression, tension. Of course, here we're only doing tension. So this leads to two methods, and they're very different methods that we talk about using this machine. One method emulates dead weight, and the other one does not. So I call this method one. I tried to come up with names. I saw these online. There are people that were talking about the different methods, but I call method one, clamp the tensiometer and adjust the force. So basically what we're doing here is we might say we want to apply 500 pounds of force. We load to 460, clamp the cable tensiometer, get a reading of 495, and then we just turn the wheel counterclockwise till our load cell reads 500.00 pounds. And then since we clamp and adjust the force value, the results are likely the same as using dead weight. That's what we've showed, right? Very similar results, because it's what it's simulating is we clamp it, shorten the cable, and then we apply the appropriate amount of force, get the reading on the tensiometer. And then there's another method. It's just clamp the tensiometer. You load to 500 pounds of force, clamp the tensiometer, and when I did this, the value jumped to 528 pounds. Now that's going to vary depending on the thickness of cable, type of cable, and all that other stuff. Though this is an example that we use, I think, a 5/16 cable. I have it later on. I don't remember offhand. So we'll get to that. So knowing these two methods, what I did is I basically compared the readings on the two. There's me, nerd, over here. This picture, for anybody that's wondering, the back, we had this drawn by a local artist. That's Mr. Morehouse to the left, and my great-grandfather, Harry Zumbrun, to the right on the mural that we had painted. Anyway, so we applied lots of different forces, 50, 250, and 500. And I used method one, clamp the tensiometer and adjust the force. Guess what? Hey, read 49 at 250, 255, and at 500, 510. If you notice that the differences, they're very close to nominal. So maybe this instrument was adjusted or spanned in using the dead weight method. Not sure. Pretty not completely sure, though I know who calibrated the tensiometers, and that's the method they use, so we can draw conclusions that that's how they were spanned in, though they might have been done at the factory as well and just sent to us. So method two is just clamp the tensiometer, 63, 270, 528. Quite a different bit of bias here, and the difference between these methods you can see at the smaller force is quite large, 22.22%. As you get closer to the actual capacity of the tensiometer, the percentage difference went down. So in principle, this all makes sense because we, shorten the difference between the two cables by grabbing it with the tensiometer. That fixed difference is repeatable, and it's close to a constant one. So we're shortening the effective length, producing more force, more tension, which then gives a force reading that's higher, right? And that's, it directly relates to the overall spring rate of the system. And I wanted to make a note here that this test used digital tensiometers, which do not typically introduce as much internal tension as some of the analog ones. It is a much softer grip if anybody's used the digital tensiometers. Like I said, we do not calibrate or sell actual tensiometers, just the equipment to calibrate it, like the load cell. We sell cable sets and the machine. So using these different tensiometers, I can have my biased opinion on them, and I can tell you that I would prefer the digital ones. By far, I prefer them to the analog ones. I think they're so much better. They introduce less tension. And I thought, you know what, for this paper, I'm just going to use the digital ones. So you can think, okay, we had a difference of 18 pounds of force at 500 on an analog one. That's going to be greater, just because it shortens the distance and puts it in more tension even more. And there's nothing great to this. I mean, there's a formula. You can draw an analogy between cables and springs. When subject to the same force, a longer cable like a spring will double the length. will experience greater stretching. Consequently, compared to a shorter cable stretched by the same amount, a longer cable may exhibit a smaller relative increase in tension. There's the formula. Fe is the spring rate, which is the amount of force per displacement. And it means if you apply 100 pounds, it will stretch 2 inches. Really, I mean, the cable length is going to be impacted here, of course. But if you think about the cable, we can see that increasing the area increases the spring rate, increasing material stiffness, modulus of elasticity increases the spring rate, and the length decreases the spring rate. A lower spring rate means less change in force when applying the tensiometer. If you think about it, just a rubber band and how thinner or longer one will stretch than its thicker or shorter counterpart. Cable is going to act the same way. Steel is much less stretchy, so the cable length changes are much less. And additionally, we're only varying the cable length from what is generally considered a minimum to a longer length, right? And in this, what I'm going to show you, we varied 3 to 5 feet. You know, depending on that thickness of the cable, those cables that are 18 to 24 inches that I said earlier will likely observe higher differences than what I'm going to show you than this 36 and 50-inch cable. So here we have 3-foot cable, exact same test, right? Machine used the same tensiometer calibration method to compare the cables, made from the same material, and method employed the clamp and adjust technique on these, right? Which kind of simulates dead weight, which means we load to, if it's 50, we probably load to 40 pounds of force, clamp it, and then adjust it in. 500, we load to 460, clamp it, shows 495, we adjust it in until it reads 500. Overall results for clamp and adjusting using different divot show similar trend that makes sense. The higher the tested value, the lower the percentage difference of the cables. You can just see, this is again 3/16 cables, which I couldn't remember earlier. So 3/16 inch cables, the difference from a 3-foot cable to a 5-foot cable was 20.4. And look, so these are different tensiometers too. So in this test point, test 1, 3/16 inch cable, test 2, 3/16 inch. In the paper I go over, I have the serial numbers of the tensiometers, but it's two different tensiometers, and you get different readings showing the exact same thing. Again, J&J Calibrations and another laboratory did these replicate tests, and these are really what we started to observe and see, that the difference between 3 and 5 foot is pretty great, and we would assume that going down even lower than 3 would produce additional error. Though you can see these regions that are affected just from varying the cable length. Here's a procedure that I pulled. It's an older procedure that ignored the bias. It's basically said, okay, the aircraft maintenance personnel would know the tension in the rig cable after the tensiometer had been unclamped from the cable. It says methodology only accounts for tension introduced by the tensiometer on 3-foot cables and applications that got induced in different cable length. As a result, there'd be very little measurement error and blah, blah, blah. So basically, 537 cable saying that there's obviously an offset to when you load to the desired force and clamp the cable. On this one, they did a 100-pound force point, and when they clamped it, it read 108. Types of cables. There's the GAC, which is galvanized aircraft cable, and SSAC, which is stainless steel aircraft cable. And then we use clamp the tensiometer and then adjust the force. So we compared both of these, 2 different cables. Performance of this Barfield indicator, look, it started at 30, went to 400, plus or minus 4 pounds from 30 to 100, plus or minus 8. And we just saw that other procedure that with the other tensiometer, it was about an 8-pound offset at 100, so that would be out of this specification. So looking at the different types of cables, I said, okay, which ones, how much is the impact, right? This is a 50-inch cable. How much is the impact between these? Not much difference. Certainly in spec. Remember, we have plus or minus four pounds of force. And then we have plus or minus 8 pounds of force, and only 1 point on the galvanized would be different. However, that's quite a bit of difference there. And the highlighted figure shows that the 1 point that doesn't meet, which would have resulted, so this is the problem. If you're using different cable, it would have resulted in a failed calibration and an adjustment when the tensiometer is actually within specification. So using the wrong cable has its own apparent risk. I'm thinking not many people are doing that because it is called out. Barfield calls it out in their manual, and some other manufacturers do. And then when you consider the measurement uncertainty of all this, the expanded measurement uncertainty at a confidence interval around 95% was plus or minus ½ pound, and the acceptance limit. So those that are metrologically astute, right? Well, what you're saying, plus or minus 8 pounds, what's the real acceptance limit? It's plus or minus 7.5 to actually, if we account for the measurement uncertainty in that case. So types of cables, there we used a same thing, 332nd SSC versus 332nd GAC, and end user must assess if their specific tensiometer meets the requirements for both cable types, considering the observed variation and their associated risk. So here on this 332nd cable, all the points were within, but you can see there's quite a bit of difference between 405.83 and 395.33. So manual for the C112A basically says in chapter 2, section 4, that using different cables will result in different results. So I showed you the procedure earlier, and I highlighted this one because this procedure, setting the force lower and clamping it. And this was the one procedure that changed. I got it reference only, not really. That's why some things are redacted, but I wanted to show it. The added tension caused by the being calibrated 3 foot is no longer ignored. So consequently, the technician sets the tension to an amount less than the desired calibration point, and then tensiometers clamped on. The amount of tension existing in the test cable is adjusted to bring the reading up to nominal point. That is the method that replicates dead weight. That is kind of the method I'm hoping to steer some of the people onto today, because if we're close to dead weight and one lab's using just stacking and actually hanging the weights that are adjusted properly for force, or however they're doing it with the associated uncertainties, versus another lab that has the same size cable, you know, clamping lower and then adjusting, those results should be much more similar than if you clamp at 100 or 500 pounds of force and then take that reading from what I'm showing everyone. That's my bias in the way I'm going with this. However, in the actual field, what do you have? You have 2 fixed points and someone goes and clamps it. So we're contending with that. If someone already has tension on an aircraft, you know, the method, dead weight method, will not give the right answer, and the right answer will be given by applying 500 pounds of force and clamping it, especially if that cable had a tension of 500 pounds and clamping it. Then you'll get repeatable results. Though I know that they're inter-switched. So we're dealing with a potential big problem here, and a lot of words that I'm saying, that we need to figure this out, right? And if I go to this, you know, right here that I highlighted, there will be a very large in the application when a particular model of tensiometer is used to make readings on 3-foot cables, but the error will decrease until it approaches 0 on cables of infinite length. And that's what this graph is kind of showing, that maybe we need some longer cables here. What we didn't get to test is we had a 5-foot versus 8-foot cable that was going to test, but the lab that could actually do this test got really, really busy with their dead weights, and we weren't able to get that. But the theory is that there should, at some point, like 5 feet, you can see it kind of on there, at some point, the cable's going to be so long that this error is going to go away. Though we definitely have it in this region from 0 to 10 feet, if you look at it. and more testing probably needs to be done on different cables and whatnot. So again, this one was using 3 foot. I know I do know Air Force uses 5 on most of their tests. So recounting cable length, just doing a little bit of recount. Right equipment, such as calibrated load cell and appropriately sized cables without defects, and following a specified process to ensure accurate tension measurements for various cable types. Crucial question still remains, which I'm going over in my head right now. Hey, you know, Navy does it the one way, they go clamp and then adjust. Air Force uses dead weight for some, uses other systems for others. What is the best method here, and what actually replicates use, and replicating use versus like standardizing across dead weight? Or are we just to say, hey, since on dead weight you cannot just clamp, you know, because you do not have 2 fixed points, it does not replicate end use, and should dead weight just be thrown out altogether? That's another thought process that you could have, because it doesn't simulate what's going on here with 2 cables that are fixed. So lots of questions. I don't have all the answers, so it's the industry needs to decide, like, look, are we keeping these methods, and what are we going to do to standardize it so everybody can make the same measurements, so we can send it to one lab versus another, and we can have confidence that they're all doing it the same way and producing the same results. Again, my bias is that dead weights probably are not going to go away, and that clamp and adjust is probably the way to standardize between labs. That's why we have committees. That's why we have hopefully maybe someone that's on this webinar and knows of another document that has a method, that common industry method. I could not find one. As you see, I found some people's procedures, though I did not find one overarching industry that says this is the way you do it. And then, are you engaging with your clients to determine what they actually want, right? Or do they want 2 fixed points where you clamp and adjust, or they want you to just clamp, right? And then look at those errors, and failing to do so could result in profound implications in one of these. If one method is used on an airplane, a pilot may complain about the rudders being too tight, which can impact the ability of the pilots to turn the airplane. So we do have consequences here on some of it. On others, look, you have a little more error on it's probably not a huge deal. It's all a risk analysis, right? Likelihood and consequences. Likelihood on an airplane, the consequences on an airplane are far greater than some of the other applications. That's all I'm getting down. So, I mean, would you want to be a passenger in a plane where the pilot's like, hey, I can't turn this thing? Probably not. So full paper here, it's MH Force cable tensiometers. You can go to documents and settings. It's got a bunch more information in it. So you can have it. It's also in the handouts here if you're on live. Other interesting notes as you're all thinking about tensiometers, cool things that we have going. We have this Morehouse Mastery Professional Development course. And what that is it's 3 emails a week. If you have not signed up for it yet, you want to know about force, you want to know some torque, all but 2 of the emails are educational, and the 2 that aren't are the first and last. And it's basically, the first is the introduction, and the last is going to ask you, hey, do you want to continue with, you know, an email a week just for a refresher? So that being said, what we've done is basically took a lot of time, crafted about 110 emails. The course runs for 35 weeks. It requires about 10 minutes of time, Tuesday through Thursday, and you get an email that explains something different about force calibration. It's the majority of its force, though we do talk about torque for maybe 10 of the 100, maybe a little more, 10 to 15 of the 110 emails. Mostly force related. It goes into load cell theory, gauging, goes a little bit deeper, goes into some of the formulas. Try to keep it on, we try generally to keep it on a technician and what a technician needs to know level. And hopefully people get a lot out of that. We do dive into a little bit of uncertainty, a little bit of this. It's really aimed at like someone that just wants to improve their force measurements and learn as much as possible. There's also a book that I have written. It's 333 pages. Most of these emails are derived in some sort of way from that book. And I've put in extra stuff in the emails and everything else. So you can see the one here, I put in the uncertainty. So just one of the emails that we have that talks about uncertainty and some of the type A's and some of the type B contributors and everything else. I know the resolution of this is not the greatest because I use snippet and copied and pasted. So if you are interested in this, again, it's free. You just sign up for your email. Not much else to do besides that. So again, that's MH Force Metrology Mastery. Other things, YouTube videos, we put some new ones up. They're okay, and then the free downloads. And if you are not following us on LinkedIn, please do, because we announce a lot of stuff via LinkedIn and social media and like to get engaged in discussions. Not everybody's on there posting or getting engaged in discussions, and we wish they would be. So